another edition of the Adventures in Sensing. This class, we actually moved to underwater. The Media Lab's been very interested in things underwater since the Oceans Initiative and work by Fadal. Lots of us are starting to really think about sensing in the oceans. And it's really such an exciting time because there's so many things, new things you can do with the advance of technology underwater. So we began with space. We had some detours to low power MEMS and so on, and now we're going into the ocean. So with that, I'll hand it off to Devora, who organized the session this week. She's a Res MVRA who is in charge of the festivities today, and I'll let her introduce the speakers and kick it off. So Devora, go ahead.
Sure. Hi, everyone. I'm Devora. I am, yes, Joe's grad student, and I am particularly interested in water sensing. I do more biological sensing, but I get very excited about a lot of the sort of technology that can go into helping people explore our oceans more, faster, better, cheaper, easily deployable, easy to use. And I initially met Brennan through the Open Ocean Initiative, which was run by Katie, who I think a lot of you here know, who is wonderful and currently on maternity leave, so I don't know if she'll make it today. But Brennan is a professor at University of Rhode Island, and he received his BS in ocean engineering from URI, took a detour at University of Connecticut, went back to URI for his PhD, and then is now a professor after doing a postdoc at Harvard. I've heard a lot about the work that he's done both in sample capture as well as the low-cost deployable cameras, and I'm really excited to get a chance for you all to hear a bit about the work that he does, and also for the class that he teaches to help students figure out how to deploy things underwater, which is great, but I don't know if we'll talk about that today. And then the next talk is going to be by Alan Adams, who is also a professor. I'll probably introduce him next, but he works at MIT and also does low-cost underwater sensing. Thank you all for being here today. We're going to record Brennan's talk, but we will not be recording Alan's talk because he'll be presenting on some work that he's done very recently, and I don't think it's quite ready to be put out into the world without being probably published and checked out. But feel free to take it away, Brennan.
Thanks, Devora. Yep, I'm not muted, right, great. Okay, so I'll share my screen in a second. Well, I might as well get going there, but thanks for the good intro. Sorry, share. Boom, and I'm gonna do it this way. Adventures with my personal boat and my 5-year-old boy there. All right, so thanks again. Yeah, my name is Brennan Phillips. I'm at URI. I'm in the Department of Ocean Engineering, but I have a joint appointment at the Graduate School of Oceanography. And yeah, I know your class is Adventures in Sensing. My talk is Adventures in Deep Sea Sensing, but I realized sort of towards the end of preparing this talk that I actually didn't focus a terrible amount on actual sensors. But I hope that's okay, because I'm going to talk a lot about ways of deploying sensors. So it's core to that as well.
Perfect.
You know, not just about the actual, yeah, you know, not necessarily the pointy end of the stick, but the stick itself maybe. And I do have some other slides I added in, if we have time, to talk a little bit about new ways to sense in the ocean, specifically at that pointy end. But I think I'll continue just to talk a little bit more about the infrastructure in terms of accessing the deep ocean. To sense and image things underwater. So a little bit of an introduction before we get too far into it. My lab here at URI is called the Undersea Robotics and Imaging Lab, or URIL, shameless promotion there for URI. I encourage you to check out my website, which is a little bit outdated by about a year, but everything on there is already published. You know, we have a lot of new stuff that isn't published that some of it I'll cover today, and just haven't gotten a chance to get up on there. So yeah, we work on a variety of topics. Image in the upper left-hand corner there is a low-light image of a Vampiroteuthis, which is a vampire squid, imaged with a ultra-low light color camera at depth. That's off the coast of Mexico. So we're able to get some really great images of bioluminescence with some of the work that I've done. The image in the center is some work that started at Harvard with Rob Wood's lab. That's a 3D printed structure right there called the RAD sampler, the rotary actuated dodecahedron. It's a really cool thing that can rapidly encapsulate midwater animals. And we have a RAD 2 coming out in the next few months, which is pretty exciting. A few other images. Actually, I think it would probably make sense to just roll ahead to the splash video. That's better than images. But we work on a wide variety of platforms all around the world. This is an expedition we did a couple summers ago in the Solomon Islands using a tugboat. So we're able to work on kind of any boat that we get our hands on to do deep sea work. We are also testing out some stuff here locally in Rhode Island. That's me on my personal boat, which you saw on my desktop when we got started. And this is actually some work just this past December. We were able to get out to Bermuda and work at the Bermuda Institute of Ocean Sciences and test out some stuff underwater there. As I said earlier, we do some work with low light cameras. Here's a view of an earlier system going down deep in the ocean, and we're imaging some really cool jellyfish. This thing is the size of a trash can that you're seeing here, so it's absolutely massive. And once in a while, we get some cool images that get on the Nat Geo or CNN. Actually, this was featured on there, and that Vampiroteuthis that you saw earlier there, just hanging out because it's being imaged with such low lights that it's not that disturbed. We also do some work on soft robotics. I'm not going to get into that today, but that's just another research theme. So ways to achieve gentle actuation at depth. Some other trade-offs are that we can do that with really low power and with really low noise. So it's just overall a much less intrusive method for sampling. And then this image right here of that 6-scale shark, which got on the Shark Week this past summer, I'm going to talk a lot about the camera that was used to film this a little bit later on today. So yeah, we have some cool stuff, and we get in the media, so you might have heard of us. Lab right now has 6 grad students and 3 undergrads. You can see everybody here except for Mike Davler. Sorry, I don't have a good image of him yet. But really great group of people who come from different backgrounds. We have software engineers, mechanical engineers, ocean engineers, that have come up through the ranks in our own department, as well as some folks who come from the Navy and the Coast Guard working with us. So that's us. Things we do in the lab, we're a deep sea robotics and imaging system laboratory environment. We focus on ways to develop new samplers for seafloor and midwater environments. As I mentioned, we do soft robotic control systems. So that's actually ways to drive those squishy fingers, as they're called, not just the finger design itself, but what's actually used to move that fluid precisely. So we actually make some of those control systems that work at depth. We work with low light cameras. And then what I'm going to talk about today mostly are low cost, simple platforms for accessing the deep ocean. And then lastly, which really digs into sensing, on the expensive end of things, we're getting into fiber optic distributed sensing. I'd be curious to know if that's a topic that you cover at all in this class, fiber optic sensing. If it isn't, I can kind of give it a brief introduction to that. All of the stuff that we do in the lab, we also take into the field. So we often collaborate with people at URI and other folks around the world for applied oceanographic research. So the projects we do are new technology that's been used to find this new thing. That type of combination is what we're reaching for. And the lab owns and operates our own deployment platforms to do this, something that makes us unique. So we have our own ROV or several ROV systems. We have a nice drop winch system that can get us really deep in the ocean. We have free landing systems. And then something I'll talk at the end are these reel-based systems that are coming online. So we're sort of a one-stop shopping a laboratory. We can develop things and get out there and deploy them ourselves. But we also collaborate as much as possible. So that's us in a nutshell. I'd like to preface the rest of this talk with the somewhat obvious statement, which is that deep sea exploration is an expensive endeavor. And so on the left-hand side, I have images of this sort of the flagship deep sea platforms for the United States. Upper left is Hercules, Bob Ballard's vehicle. Upper right is Sebastian, which is Schmidt Ocean Institute. In the middle, we have Jason, which is operated by Woods Hole Oceanographic. Doc Ricketts, which is operated by Mbari out in the West Coast. NOAA's Deep Discover ROV, that's the one with the white foam. And of course, Alvin, which is the manned submersible based out of Woods Hole. These systems cost millions, if not tens of millions of dollars to develop, and then an annual budget that are in the millions to operate. Not only that, but the vessels that are used to operate them are very large scale. So there are more than just this, but of course there's the EV Nautilus, Bob Ballard's boat, vessels like the Atlantis out of Woods Hole, which runs both Jason and Alvin, the NOAA ship Okeanos Explorer, and Schmidt Ocean Institute's Falkor, which is now about to be replaced by Falcor 2, which is 3 times the size of that boat in the bottom right-hand corner. So these are massive operations that, again, cost tens of millions of dollars to develop and then operate. They have very large operating costs to get them out there. And I'm not trying to trash them too much. I used to be the lead operator of Hercules, and I worked on the Nautilus for about 6 or 7 years of my life. So I love them, and I have deep personal relationships with these robots. But I also totally get and understand some of the challenges that we face with using them and acquiring them. So some more obvious statements. Okay, this stuff is expensive. It's also really big. Why is it big? Well, any of those remotely operated vehicles that I showed earlier, with the exception of Alvin, which is a sub, so it can fly on its own, but they're all operated using a tether or an umbilical that's connected to the surface. That umbilical usually has fiber optics, which is pretty small stuff, and then electrical conductors for powering the vehicle for as long as you want. And that's pretty chunky. So Hercules, to use that ROV as an example, is a 4,000 meter rated ROV, and therefore it has 4,000 meters of tether. And that's what this looks like. This is 4,500 meters of the ROV's umbilical. It's 0.68 inches in diameter, and it's put onto a winch that weighs about 14,000 pounds. So here's an image of the winch, and you just get an idea of the scale of that. And that is a tiny winch. True story. That is a small oceanographic winch for ROVs. I've been to the winch manufacturer locations before. Dynacon, which is in Texas, is a major one. And our little winch is kind of wimpy compared to some of the big ones that are out there used by the oil and gas industry. Okay, so the cable is core, and that's really something I'm going to harp on in a little bit. It's all driven by the size of that umbilical. That tells you how big the winch is, and that tells you how big the boat is to operate it, both for its size and weight, but also the power needed to drive it as well, right? You need a massive main engine or generator system to power these systems. Big gear means a big boat. Big boat means more expensive platforms, more expensive operations, right? Dozens of people to operate them. And that ultimately equates to more limitations on when and how much we can explore our oceans. These vehicle systems like Deep Discover that you see here, this is a shot of the back deck of the Okeanos Explorer, and you get an idea of the scale of everything, right? You have to climb a ladder to get on top of this 9,000-pound vehicle, the A-frame, the shivs, everything. It's just massive, massive stuff. Extremely capable, but they're only able to go at one spot at a time. And so if I can go to a slide, I'll just jump back and show most of the US scientific deep sea fleet in one slide. Well, that just tells you how limited we are, right? This is it. And we can't operate all these all the time. So they have downtime and everything like that that's associated with it. So it's a limitation from my perspective. So to address this, we now have the lingo is deep and cheap, right? This is a real emerging trend right now among folks like myself, Alan Adams, who we'll hear from soon, hopefully, and other people at MIT and around the world are all coming up with ways to make things that work underwater smaller, lighter, cheaper, so that we can get more of them, so that we can deploy them easier, right? We can spread the word out. Other people can attain them besides just people who have money, lots of money. So the industry, just to put it out there, the commercial industry is really leading the way in a lot of.
Don't worry, there's no camera. I'm just watching.
So Blue Robotics, which is a really great company, I encourage you to explore their website. Blue Robotics is based out of the West Coast, and they make a vehicle called the Blue ROV. That's what you see right here. For about $4,000, you can buy that yourself, or you can buy it as a build-yourself kit. This thing can go 100 meters deep, and it's expandable. Like, you can plug in your own things. There's a network hub in there, so you can add on your own cameras and devices and that sort of things. Also, one great thing about Blue Robotics is that everything you see in that vehicle, you can buy from them a la carte. So you can buy the thrusters, you can buy the cameras, the housings, the tether, and make your own system. So Blue Robotics is really kind of at the apex of this right now commercially, with all these things that you can go on and buy it now with a credit card type stuff. So there's companies like that. Starati on the right-hand side makes biologging instruments. So things that be used in animal tags, or maybe implantables you might put into a shark or something like that, if you can get your actual hands on there for that. And you can see the scale here, but they make these instruments called DST millis, DST centis, that are the size of a couple segments of your finger. You could almost swallow them. And like the DST Senti, for example, measures conductivity, which is salinity, temperature, and depth down to 3,000 meters in a self-powered, self-logging instrument. Again, that's the size of 2 segments of your finger. So that company is really cool. They have more products than I'm just showing here. They're based out of Iceland. So you see the biologging community kind of jumping on that because they need things to be small. They want them to be cheap so that people can have more tags that are out there. So this is really cool technology that I use. And then another company that's out there, and there are other groups like this, Group B Inc., which is based out of Florida, makes a deep sea GoPro housing, which I've used a lot in some of my early work. GoPros are actually really awesome for the price point, really great optics. And if you can buy a nice deep square housing like this for $500, it's about how much they cost, you have a very cheap, affordable imaging system that can get you really deep in the ocean. So this is some of the flavors that are out there right now, commercially available for deep and cheap type stuff. So we make a lot of our own deep and cheap stuff in my lab, and that's what I'd like to talk to you a lot about today. So one early thing that I did, this is back when I was doing my PhD work at URI, I had to do a project out, or got the opportunity, I should say, to do some research out in the Solomon Islands, which is a really interesting corner of the world. There's thousands of islands with really deep water within a stone's throw. Like there's just sheer cliffs literally that go down hundreds, if not thousands of meters of deep within eyesight, or sight of shore. And so I went out there to work with some work sponsored by National Geographic, working on whatever boat was available. These are really small boats, in some cases, open boats. And my approach was to take an electric fishing reel and wind it with some really optimized fishing line that you could buy, 250-pound hollow core braid, as it's called. And I was able to fit about 2,000 meters of that onto this electric fishing reel. Very simple. Then I made my own platform, which you see on the right, which was a down-looking camera system. There's the GoPro in the center, that black cube, with some potted lights, LED lights that were potted, a depth sensor that was more expensive, but I just happened to have it, and some flotation to keep everything upright. And so I was able to use this on multiple deployments. I was able to get at least 1,500 meters deep, but just some example images from a little bit shallower here. We get pretty good shots of the bottom like this. I had video as well. And so this is at its basal level, just early exploration of some areas that we've never gotten imagery of, right? In some spots, working off of really small boats with battery powered GoPro type deal. So that was pretty neat. And I've been kind of thinking about fishing reels ever since, because this was like a big aha moment. Wow, I can buy this small lightweight thing that folds up in a suitcase, and from whatever boat I can get on with a 12-volt battery, I can get down there and bring it back. I've then since moved on, and for the past few years, I've been sort of homing in on these do-it-yourself BRUVs. BRUV is an acronym for Baited Remote Underwater Video System. So these are cameras. There's all kinds of variants of BRUVs out there, often used in shallow water for things like assessing shark populations because they like bait. But there are deep water BRUVs as well. And so this is my low-cost do-it-yourself BRUV that I developed and optimized that uses some deep flotation spheres, a battery housing, GoPro lights, and an acoustic release. So these things are thrown over the side from whatever boat. It takes about 2 people to put them over the side. And this acoustic release that you see down here in the bottom, this yellow tube, has a little mechanical drop system that's attached to some expendable weight. So I use these kettlebells, for example, but you can use anything. I've used old disc brakes, or sandbags, that type of thing. So you send this down, and with that weight, it's negatively buoyant, it sinks, it lands on the seafloor. Here's a shot of these things. They're free falling. And then when you send a command from the surface, it will drop the weight. The rest of it is positively buoyant and will rise back up to the surface. So you can leave it down there for however long until you send a signal for it to come back up. And so you can see this thing landing on the seafloor hundreds of meters down. This is some footage from the Bahamas. And we get fairly decent imagery. Again, the price point of a GoPro is pretty good. So this is 4K video, probably subsampled here, of some deep sea sharks. And so we can learn a little bit about population dynamics. Maybe we'll make a new discovery this way, at least observe their behavior in the deep ocean and get an idea of what's down there using a very simple system. And that free falling lander system that I showed you, I've made a bunch of them. Right now, my price point is around, to go back, $11,000 to make one of these. 7,000 of that is that acoustic release right there. So I'm working right now on finding ways to get around that. As wonderful as these things are, they work really well. You know, of course, I want to get this price point even lower. But in the meantime, I've been focusing more on the cameras and the lights and finding ways to make those smaller and cheaper myself. Because a GoPro is, depending on the type you buy, but by the time you're done, it's maybe $300 or $400. And then you have to buy the housing, that's another $500. So that's $1,000 just for the camera. And to me, that seems a little bit high for some basic video. So I'd like to get a little bit lower that. So to do that, I've been employing some new techniques that make heavy use of additive manufacturing or 3D printing, specifically stereolithography. So you guys being at MIT, I'm sure you've seen Formlabs printer wandering around there. I'm a Formlabs lover. I have 4 of these printers. I just got my new 3L, which is pretty exciting. And if you aren't familiar with stereolithography or SLA 3D printing, what's special about it is that it prints fully solid parts that have really good mechanical properties. So we're talking things that have yield strengths in the 3,500 PSI range, which is pretty good. You know, a lot better than anything that FDM printers can produce, or even powdered fusion. So SLAs are sort of my fave for that reason. This image right here, maybe some of you recognize if anybody did any COVID response work early on in the lockdown period. These are 3D printed Y splitters for ventilators that we were able to produce because, again, they're fully solid and have really nice material properties. So I really like these printers. Another quick tangent is that we've been able to take them to sea. So we published a paper last year with some students that, some seniors actually in ocean engineering, made a stabilization system for one of these 3D printers. And so we were able to take it on a vessel. This is the URI boat Endeavor. This is inside one of the labs there with a printer at sea. And they would go out, they did 2 different expeditions with this stabilization system and 3D printed their own pressure housings that have integrated O-rings and everything like that. So that was something that they started. And this was like a basic depth logging system that they made. 3D printed housing, electronics put together, very simple, you know, whatever, at sea. And then they were able to send it down to 200 meters. So from soup to nuts, they developed this out on the boat, not in the laboratory. So changing that workflow is sort of the idea there. So you can check out that paper if you're interested in how he did it. But you know, that's the idea, is we're taking a lot of this stuff out into the field even more, trying to develop and iterate in the actual environment. So believe it or not, based on some of this work that the seniors did, where they were the first ones that I had worked with to actually 3D print an O-ring, I got the idea in my head that I could use that to make camera systems. And so that gave birth to DPi, which is a whole range of products now that my lab has made based on Raspberry Pis and Raspberry Pi cameras. And so here are some variants that we have made at this point. Upper left is DPi Pro that we call it. It's a fully integrated self-powered Raspberry Pi with a camera that has autonomy. So it's self-logs, self-records, rechargeable type system. The one in the upper right-hand corner is a Pi 4 with live Ethernet out. So we actually have an Ethernet cable that you can plug into an ROV system. So if you want a live feed from like an IP camera, that's something that we've made. And we've made full multi-camera arrays at this point. So this is a 4-camera system that you can see right here, attached to, it's not shown very well, but a 5th Raspberry Pi that has its own camera as well. So it's actually 5 cameras, all on a single network stream. And so all this stuff is based on the core design of the camera itself, because potting electronics in its most pure form is really not that groundbreaking. We're just doing it better with 3D printed molds. But the camera is new. The way we do the camera in the imaging sensor, well, you can't pot the camera itself. You can't pot the lens assembly because you'll violate the optics that they're designed around, right? So you have to maintain a little bit of an air gap. So this cutaway view in the middle shows you how we do this. We print a 3D print, excuse me, a shell, and then we install the camera board in the center. And with these injection ports that you can see here, we pour epoxy, or inject it, I should say, just up to the lip of the, where this red part is, just up to the lip of where the lens comes out, okay? And then we have a 3D printed O-ring seal on top of that with a piece of polished glass. I was able to buy these for 20 bucks, and you can get them readily online. And that is a really tiny deep sea pressure housing. And this thing I've tested down to past 5,000 meters. So pretty awesome. I was surprised myself that it worked, but that has allowed us to make our own individual camera heads and then all these other variants that you see here and beyond. And because it's 3D printed, we have full control over the design, right? So at its basic form, it's a cube, but we can print it into any design we want to, integrate it however we want. So we really have full control now of how this thing is shaped. I'm going to take a pause here because I'm seeing some chats and I'm wondering if they're for me. And I'll take a moment to answer them. Are these wired or wireless is one question. Well, they can be both. So to go back here, I'm sorry. This camera here in the upper left-hand corner doesn't have any live telemetry out of it when it's underwater, but it does have a Wi-Fi antenna. So if you can get close enough to it underwater with a Wi-Fi router, like within a couple inches, you can get live telemetry through it. And we've tested that. This one over here is hardwired with a real Ethernet out. So as long as you have an Ethernet connection to the surface, like again, through an ROV, then yes, they can do live feed through that. Same for this array. It's meant to be a live feed system. Another thing I'm seeing here is that Formlabs is an MIT Media Lab startup. It might be. That's awesome. Formlabs is great. So yeah, they're a really cool company, and we've been able to work really closely with them over the years.
Brennan,
Okay.
are the DIY bruvs also wireless?
Yeah, and they don't have live data transmission. So if you go back and watch, this is shameful, but the episode from Discovery Shark Week last summer was Tiger Shark King. I know. But if you watch it, it gets even worse. My bruvs are featured in there showing live video from the deep ocean. There's no way that could have happened. So they go down, they see something cool, but you don't know until you retrieve them later and download the data. So we could do wired, but you need the cable. We're going to get into that a little bit more in a minute. So yeah, thank you. Thank you, Novi-san. It's quote unquote live. Okay, so just a few other examples of what we've done with DPI, and there's more beyond this. Here's some early images. Some of the first video we ever collected in Bermuda at depth. You know, we're limited by what a Raspberry Pi camera is. They're not that great. And I really wish that we could break into some of the cameras that we have in our smartphones. It comes down to the cables, the little tiny ribbon cables that attach to those sensors, the drivers, those are super proprietary, right? Samsung's competing with Apple and yada, yada. So Raspberry Pi is great because we can access it and work with the actual OEM parts, but they're not that great of a camera. So we're really held back right now by what is commercially available. But if you have any ideas on how you'd like to collaborate, maybe with a better small camera that you know how to control, please email me. I'd love to talk to you. Okay, yeah, so here's just some video we've done with that. Here's an early version of DPI Pro that we used on a landing system off Endeavour at 3,300 meters. That showed us that we could directly pot 18650 lithium batteries and they would survive that pressure. So that was pretty cool. And we've also used DPI to guide benthic grabs. So a couple years ago now, we worked with Roxanne Beinart, who's a professor here at URI. She was interested in chemosynthetic mussels located off the east coast of the United States. And I said I had a nice cheap camera system that could look downwards while they were doing these benthic grabs and sampling. And so we have sort of live view to do that right here. And there's these sort of basic stainless steel arrays that I made here with a fiber optic transceiver to the surface. Now, I want to take a minute and look at this image on the left-hand side. Here's a benthic grab. That's that same thing you saw in the video here. Let me play it again. Okay, so that's that thing that's underwater. Everything that's above the surface right here is a really simple frame that I had made up, and it's all around putting a fiber optic transceiver inside a pressure housing. There's a battery somewhere on the other side, and then there's 3 DPIs on the outside of that housing communicating through wireless to a router that's on the inside of the housing. Okay, That router is then converted into fiber optic telemetry, which is shooting up this cable out of view to a winch that's topside. I will tell you that the winch itself is about the size of a pallet. So it's like 4 feet by 4 feet by maybe about 4 feet tall, sorry. And it weighs about 3,000 pounds. So that's a pretty small deep sea winch, 3,000 pounds, 4 feet by 4 feet by 4 feet. It's not really that small. You can't put it in your car. You can't fly with it and check luggage. And you still need a big boat. I mean, something that has a steel hull and a large generator to operate. So at the time I made this system, which is about 2 years ago, that was the lowest common denominator, the absolute smallest way I could get live feed video from the deep ocean. So we had a little bit of a breakthrough. So I can talk about this now because we just had a paper come out in Sensors a week and a half ago. And it's about the fiber optic reel system, which we dubbed for reels. That's the acronym we pulled out of there, for better or worse. So remember that fishing reel I showed you? I used in my PhD to send down a GoPro that was self-logging. Well, I got the idea in my head. What if we took that fishing line, which is hollow core braid? So if anybody's, if anybody fishes in the audience, you know that braid is this really nice, very lightweight line that you can use. And it's like a weave. It's like a really delicate weave. And if you get the heavy duty stuff in the center, there's a hollow core through the center. I thought to myself, why couldn't we put a fiber optic in there? And if we did that, then maybe we could get live video over fiber through a fishing reel. So we did that. I'll come back to this image so you can look at it again in a minute. But the invention was this stuff called fiber optic fishing line, or FOFL, as we call it. So a few different shots on the left give you an idea of the scale of what this stuff is. I'm working with a company called Nautilus Defense, which is based out of Pawtucket, Rhode Island. They're a textile manufacturer, experimental textile manufacturer. So we're lucky to have them here. I approached them with this concept idea and they said that they could make it. And we've gone at this point through probably 4 or 5 different design iterations. This right here, the bottom left-hand image, is what 1,200 meters of fiber optic fishing looks like. And you get an idea of the scale with the quarter that's right there. The other invention that we had to come up with, you can't just tie a knot with a fiber optic line because it'll break the fiber. It'll break the fiber optic. Okay, so that's not going to work. You need to come up with a mechanical termination that isolates the loading, the weight loading, from the actual fiber on the inside. And so this cartoon in the diagram in the center is a diagram of what this thing on the right is. That's the mechanical termination. Again, it's Formlab's 3D printed part, so rapid design iterations that we can do directly in the lab. We have FOFL coming in, and then it hits a stainless steel tube that goes through the whole center of it. You can't see it up here, but it's coming out of the bottom of the housing down here. And that's a furcation tube. So if anybody does fiber optics, you can furcate fiber optics from their buffer. And that's the idea of spreading it out. So the fiber optic itself goes into the tube and is protected. The outer load-bearing fibers go on the outside of the furcation tube. We then insert it into that 3D printed part, and then we inject epoxy again into the center and fill it. And what you end up with is the fishing line itself, like the actual hollow core braid, becomes bonded to the 3D printed part, and the fiber optic goes right through the center and comes out through the bottom, not under tension. That's what a mechanical termination is meant to do. We just made a really small one. So we filed patent on this whole thing, and that's all described in detail in that paper that I'm pointing to you right there, which is open source, or what do you call it? Yeah, it's open source. You can download it freely to go with it. Now remember that DPI camera that I told you about, right? The idea that you can epoxy pot your own electronics. Well, that becomes part of this as well, because we can make our own size optimized, weight optimized camera system on the end of it, or let's just call it a network solution here, because it doesn't have to be a camera. We just went for that right away. So we can take, a 3D printed mold, put the Raspberry Pi fiber optic transceiver, battery, and everything into that. This is an early prototype that we made. We have a newer version that looks much better with a light. That's this, sorry, I thought I got rid of all my labels, but F is a light that's coming out of there. And here's this sort of payload that we made. So it can be powered for about an hour, it can run on its own, and it's transmitting gigabit Ethernet up the fiber optic, or back and forth, I should say. And it's now an integrated payload that's of the size gauge as fishing line is. And so here's some example video that you can download too with the paper. This is the supplemental material. There's a little bit of sound here. We're working on a center console boat here this past summer. This is like late July during the pandemic. Working on I think it's a 32-foot boat center console out here, about 100 miles offshore. Here, I'll get the sound out of the way. And you can see the size of this system, right? It's just a little small thing sticking into a board that we mounted on the back. And this rough video is live video from 350 meters that we're seeing on the surface. And I'm actually paying in and out based on what I'm seeing in the live feed. So I'm now a human in the loop control, making sure that I'm not crashing into the bottom. Well, I definitely do crash into the bottom during the course of this. And oh, sorry, there's sound here. But that's an idea of what this thing looks like when it's running, paying in and out. We've since taken this system out much deeper. We've taken it out to Bermuda and we had it down to 780 meters. So again, live transmission from a 12-volt battery powered system that you can fly in your suitcase and deploy on literally any boat platform you want. That upper right-hand screenshot, that's the live view that we get in a browser topside. So that's what we get to see when we're actually operating this thing. So pretty exciting that it worked. A little bit of bioluminescence at the end that we got out of there. And then just to go back to this image, again, this is what it looks like. There's that electric fishing reel. Here's a fiber optic slip ring that we mount to the side. It's a really small slip ring that we can get commercially available. And then the fiber optic line goes out. It goes over this sheave, which is a bike wheel. And we're moving past the bike wheel now. And then here's that payload that it sits right here, but then we just basically let it go and it goes freely, and then we can send it down, up and down on there through the whole system. Sorry, I have to go past that. So that's really where I was going to stop today. I just wanted to give you an idea of where we're going with the lab, which is really at this point, we're starting to synthesize a lot of the work that we've done. We're taking that epoxy potted Raspberry Pi type stuff or microcontroller, just to be agnostic about that. And we're applying it to this really nice fishing line system that we now have and moving towards fully deployable human in the loop systems that could be deployed from literally any boat. And so getting away from that big ROV, big ship science, we're enabled to do that. So with that, I'm going to stop and take any questions because I realized I talked for probably my time here. But yeah, please fire away with any questions you might have. Thanks for the shout out. I see in chat, but please go ahead.
Maybe I'll ask this wonderful talk. Maybe I'll ask a quick question. You talked about an acoustic release. Is that an acoustic command you send down through sonar to tell the thing to release? And if that's the case, do you have a backup where if there's a watchdog timer, if you don't get it in time, it'll scuttle the ballast and come up anyway?
You can do all those things, Joe. Yeah, I'm not as sophisticated as the backup option, but yeah, you send a very low frequency code from the surface saying time to release. It sounds like a bird chirp, 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 because it can transmit really far underwater that way, and then it drops the rate. But yes, you could definitely put things like a magnesium link in between, because magnesium will corrode at a predictable rate, relatively predictable rate instead. There are other systems that are timed as opposed to commanded from the surface. Yeah. Another question I saw in the chat, just so I address everything, was, do I see any problems with the Formlabs resin when it's submerged underwater? The answer is no, I have not seen any problems with it. When it's fully cured going into water, it seems to be totally fine. I think if you leave it in alcohol for too long, it doesn't like that. You do wash it with alcohol, but I think long-term soaking in alcohol isn't so good. But seawater seems to be totally fine. And we're about to do a 1-year deployment, so we'll really find out.
Maybe one other quick question. You had your ribbon cable coming out of your potted sensor.
Mm-hmm.
And how do you seal that? When I've had cables coming out of potted sensors, that's a weak point, and water will find its way in. So you've got to have something else to prevent that, I would think.
Yeah, so that's speaking from experience there. It really depends on the material of the wire or cable that is coming out of there. The only one that I have found, Joe, that's really problematic is silicone. It's really hard to bond to silicone.
That's what we used.
Yeah. So if you're going to use silicone, you pour Sol, but there is a way around it, and we can talk offline. I found a couple solutions that seem to be working. But neoprene jackets, Teflon jackets, any of the buffers that are on standard fiber optics, totally cool. But the silicone jacket, that's something to be a little bit worried about. And there are a number of things you can do to get around that. Yeah.
Hey, Brennan, thanks for the talk. I was curious, I might have missed this, but how do you actually process the fiber optic data on the Raspberry Pi? Is there some sort of modem on either side of the actual fiber optic transmission cable that kind of like converts it into and out of binary or something?
Well, so I just buy off the shelf network to fiber converters. So for
Gotcha.
$100 or less on Amazon, you can go find, gigabit Ethernet to fiber optic converter, and you can buy these little boxes. I open the boxes, I pull out the electronics, and I put them into epoxy. I have a few choice ones that I like that have less capacitors involved. If you're really sharp, you can replace the capacitors because those have air volumes that can implode. But really, I just put the Ethernet out of the Raspberry Pi and remote desktop into it. Is the way I go at it.
Gotcha. So on the Raspberry Pi side, the interface with the fiber optic module is via Ethernet cable as opposed to like UART or USB or something?
On a Pi 4, yes. On a Pi 0, if it sounds like you're working with here, Pi 0s don't have native Ethernet out, which is a problem. But you can get around that. You can get IP over USB. And so there are USB to fiber optic converters. We have a few of them that we've been playing around with in the lab. They work. So depending on the flavor of Pi you're working with, you have a few different options at your disposal.
Very cool. Thanks.
Yeah. No worries.
Quick question on power budgets and stuff. So a couple of times you've referred to the modules as self-powered. Is that like batteries or actually some like energy? Okay.
Yeah.
What's the kind of the power budget of a module, and so the kind of the lifetime that you get before you need to charge?
Right. Okay. So I generally break rules. And one rule that I break is I take 18650 batteries, right? The standard vanilla flavored cells, and I just pour epoxy right around them, and they work to depth. And I've been doing that for a while without any problems. So my favorite is a dual cell 3.7 volt, 4400 milliamp hour thing from Adafruit. I really like those. That, depending again on what you attach to it, it gets me hours of runtime. I'll just, be rough like that. I'm a little bit hesitant to pot many more than two 18650s together, although I think it'll be fine. I don't know. I would lean towards maybe putting them into an actual dry pressure housing to be a little bit safer, which we can 3D print ourselves, of course, or we can use a real pressure housing. It might, at some point, if you really need a ton of power, you might want to pair a low-cost sensor or camera with a more expensive, really good power system. It's not always going to be purely cheap.
Yep. You mentioned you have like a year-long or scale deployment coming up. Is that still going to be battery powered, or? It is, but that's in partnership with another group at Harvard with Pete Gerges. That's a larger lander system. To describe it, I think it's like 3 meters by 3 meters square. If you can imagine like a platform that sinks in the ocean that is sitting there for a year monitoring things. And that is powered using lead acid batteries, large lead acid batteries that are pressure tolerant. So they get a lot more power out of those. They'll have multiple of those in an array. So probably hundreds of pounds devoted just to power for that thing to last for a year. Well, thanks.
No worries.
Great. Actually, I have a question to follow up on that. First of all, great talk. And I wonder, have you seen or have you used any hydrokinetic energy kind of this kind of transducer or things that can harness the energy of the ocean waves, for example?
No, but I want to. So I'm open to collaboration or any ideas there. And I mean, you just described like probably a whole other lab that's working on stuff like that. We don't undertake that ourselves, but I'm definitely interested. I'm aware that the fact that we send something down from the surface to 3,000 meters and we don't get energy out of that, I mean, that's a waste of a lot of potential energy. So there's some way to use that to our advantage, and I'm not working on it yet, but there is a way. There definitely should be. Yeah.
Okay, thank you.
Yeah, sorry, it's not the best answer because there's a whole box to open there.